Hopefully they're tranquilized first. Okay. All right. Listen up. Okay, let's take a quick look at this. We went over the formula for simple interest, talked about interest is money you get paid or that you pay for the privilege of borrowing money. Simple interest was very easy. It's just the interest that you get is the principal times the rate times the time. That P, R, and T are used all the time. You want to make sure you know what they are. We then went through and we came up with a formula that would tell you not just the interest that you're paid on simple interest, but the total amount in the account. So we get 100% of the principal plus a certain percentage rate times the time, and we ended up getting the same answer both ways. So this formula is pretty useful. And then we started talking about compounding interest. When we say interest is compounded, what we mean is interest is paid to you and then added to the account. Or if it's a loan, interest accrues and it's added to your account. Makes a huge difference. So we went through an example. Same $1,000 put in an 8% per annum or per year account for 50 years. We said at the very beginning there's 1,000. Then it's going to be 1,000 times 1 plus 0.08. That's 1080. And we said for year 2 we could take that 1080 and multiply it by 1 plus 0.08. Again, 100% of what was in there and plus 8% more. Or we could represent the 1080 as 1,000 times 1 plus 0.08 and then multiply it by 1 plus 0.08 again. And do it again and again and again. So what happens is when we want to figure out how much is in there after 50 years, it's going to be 100 times 1 plus 0.08 raised to the 50th. That's compounding every single year, and we ended up with a ton more money. At the end of this, it was only $5,000. Because they compounded, paid us a little bit of interest every year, and put it in the account, that adds up to almost $47,000. So a $42,000 difference. Okay? And this is the way interest works. It's not simple interest that we generally work with. It's compound interest. Okay? So a very, very powerful principle. If any of you have a parent or a sibling or somebody who's a financial planner or in finance or something like that, compounding makes a gigantic difference. So what we did is we tweaked that formula just a little bit and we said, well, you know, it's not very often that we just get paid or pay interest once per year. Normally we have like monthly rates or monthly payments that we have to pay. If you have a savings account, normally they put money in your account, a tiny bit of interest every single month. So usually it's compounded monthly or quarterly or something like that. So we went through an adjustment and we said, look, they're not going to pay us the full interest rate. What they'd do is they'd figure out how many times do we pay per year. If it's monthly, that's 12 times per year. So we take the interest rate and divide it by 12. But that means they also pay us interest more times per year. So that's why we take the exponent, the time, and we multiply it by that same factor n. So the only adjustment that we have to make on our little formula right here, this one right here, is we're going to divide the interest rate, and then we're going to, or this one right here, I suppose, we're going to divide the interest rate by n, and we're going to times the time by n as well. Yeah, it's this one right here. Okay? So we went through and we did several examples where we compounded quarterly, monthly, daily, hourly. We could do it per minute and so forth. And the idea was we could get to a point where we're continuously paying interest. We're continually compounding interest. And the formula is PE to the RT. So that's the natural number E. It's a little more than 2.71. So we just type in the principal, E, raise it to the number, raise it to the interest rate times T, and that will spit out the answer. It makes a bit of a difference here. In this case, it made what, a $700 difference or so? Okay. So not a tiny amount. I mean, I'd take the $700, but it's not as big a difference as when we go from simple interest to plain old compounding interest, or going from monthly, monthly to quarterly. I mean, that made a fairly significant difference. Okay, are there any questions on what we talked about last time? All right. Then you've got some problems on your assignment like the ones we went over, and you've got some on there like this. So it says compounding is much better than simple interest because it has the effect of making the interest rate appear higher than it actually is. So in every one of those cases, the interest rate was 8%. And yet sometimes we ended up with more money. We ended up being paid more interest. Okay, think about that for just a second. If you were paid continuous interest at 8% for 50 years, your $1,000, just $1,000, mow a bunch of lawns over the summer and put $1,000 in an account like this, and at the end of 50 years, you've got $55,000. You've got $54,000 in interest. Okay? Huge amount of money. Okay? But it was all based on 8%. So we've got the difference between way up here, $5,000, $47,000, $52,500. Okay? It has the effect of making that interest rate appear much larger. Why did this $1,000 go to $55,000? Because of that compounding. Again, compounding makes the interest rate seem bigger than it actually is. So one of the words that we use for this is we use the word effective rate. What is the effective interest rate? Because you're compounding, it's going to be a little bit more than 8%. Can you tell me what that effective rate is? Or sometimes you'll hear the word yield. How much interest does it yield? What's the effective yield? Okay, now I think this is the easiest way to compute the effective interest rate or the effective yield. Use $100, because that's kind of like a percent, 100%, okay, as the principal and 1 year as the time. And then what we're going to do is we're going to take a look at this and we're going to compare the answer with what we call the nominal interest rate, or that's the original rate, the normal rate, okay? So in this example it says, what is the effective rate of compounding 8% quarterly or continuously? So again, you've got to know the key words here. You've got two formulas to choose from, compound interest and continuous compound interest. This is the one you use unless they use the keyword continuous. If they say continuous, we're going to use the one with the E in it. Did they say the word continuous here? Nope. So we're going to do A equals, how much money did I say to put in if you were going to figure out the effective rate? $100. So we're going to put in $100. Then it's 1 plus, let's see, 8%, always as a decimal, so 0.08. And we're going to compound quarterly. So if I compound quarterly, what's N? 4 times per year. So we're going to divide by 4. And then how much time did I say to use? 1 year. Okay? Very simple. $100 for 1 year. Plug it into the formula. So let's grab the calculator. And we're literally going to type that formula in there. So it's going to be 100 plus, or times 1 plus 0.08 divided by 4. And then we're going to raise that. What's that? No, order of operations. If you want to put it in there, it's not going to hurt. But it's going to do the division before it's going to do the addition. So you're going to get 1.02. Good. And what's the exponent? Exponent's of 4. Okay, now, we're being paid about 8% interest. It's being compounded though, so it's going to make the interest rate look like it's a little bit more. So we're expecting an answer that's a little bit bigger than 8%. So now take a good look at this. How much did we put in? We put in $100. How much is there at the end of 1 year if it's compounded quarterly? $108 and 24 cents. Not 108 even, not exactly 8%. All we have to do is take that 1 and the 0 off. It's going to be 8.243%. Because it was $108, 24.3 cents. It was like this. Subtract the $100. What was the interest? $8.24. So what's the effective interest rate? 8.24. Okay. Now pay attention to the instructions. Sometimes it'll say round to the nearest hundredth or something like that. Okay. I like going at least 3 decimal places. Okay, are there any questions? Okay, that's compounded quarterly. What's the key word right here? Continuous. So we're going to use this formula. A equals P e to the RT. So on this problem, $100, 100, e to the 0.08, how many years? Just 1 year. So on the calculator, we're going to type in 100. Grab the exponential base e, and we're going to type in 0.08. If you want to times it by 1, that's totally okay, but make sure everything that's in the exponent appears in the exponents in parentheses and all that sort of stuff. Now, are we expecting a number a little bit bigger than 108.24 or a little smaller? A little bigger. Why? It's continuous. They paid interest more often. So that makes a difference. We go from 8.24% to 8.32%. Okay? So 108, 32, what was that other one? 3287? Okay? So that means the effective interest rate was 8.32. I'm going to put a 9 there. Okay? That's the effective interest rate. Now, Snup, if you were a bank and you had a choice, would you say, let's say you compounded quarterly, would you tell your customers that you're paying them 8% or would you tell them you're paying 8.24%? You tell them 8.24 because it sounds bigger, right? People like that. And that's okay as long as they disclose that it's an annualized rate. Sometimes they'll call it yield and stuff like that. There are rules about how honest they have to be or the way they need to present things so they appear to be honest. Okay?
I have a question.
Yeah.
It was like 8.9%. Could they round it up to 9?
I don't think so. Okay. I think they have to go to like 2 decimal places. Not sure. But there's a rule on that though. Any questions? Okay. So you will have some problems that talk about something called present value. They'll say, go ahead and compute the present value of this. So what present value simply means is how much would you need to deposit into an account now? Or in other words, in the present, in order to have a certain amount later. So this is like retirement planning. Everybody wants to be a millionaire. How much principal do you need to invest now to have $1 million in 50 years if you've invested it at 8% compounded quarterly or 9% compounded continuously? So let's figure this out. How much do we want to have? We want $1 million. Now the key word here is it's compounded quarterly. So we're going to use the one that's A equals P 1 plus R over N raised to the NT. And here's what we've got to do. We want $1 million. We don't know how much principal we would need to put in right now. And then this is 1 plus, it says 8%, so 0.08, compounded quarterly. That's going to be divided by 4. And then this is going to be 4 times, how much time did we say we have? 50. Okay, now, if you take a good look at that, that's kind of ugly. We'll clean it up in just a second. How many variables are there in the problem? There's only one. We ought to be able to solve this. Okay, now, how much would we need to put in now to figure out how much? Let's see. We want $1 million. So if I put, when I'm done with this, we're going to know how much principal we'd have to put in right now so that at 50 years from now, you guys are 16, 17-ish, maybe 18. 50 years from now, you're going to be in your late 60s, about the time you'd want to retire. Do this and you'd have $1 million, right? So let's see what it is. I'm going to clean this up just a little bit. This is 1 million. This is the principal. We don't know what it is. But this is 1 plus 0.02 raised to the 200th, right? 50 years, pay interest quarterly, 4 times a year, 4 times 50, 200 times they're going to pay us interest over those 50 years. Okay. Let's see. What do I need to do? Just solve for P. That means we need to divide, right? So I'm going to divide by, this is just a number. This is 1.02 raised to the 200th. 1.02 raised to the 200th. Those are going to cancel, so I end up with P equals. So if I grab the calculator and type this in, 1 million, so 1 followed by 6 zeros, then we're going to divide by, and I am going to put this in parentheses just for the heck of it, 1.02 And then we're going to raise that to the 200th, right? What does that mean? Somebody say that for us? $19,053. So, if you could scrape together $19,053 right now, put it in the bank or some account that would give you 8% compounded quarterly, you'd have $1 million when you retire.
But where are we gonna find something?
Rich uncle.
Don't banks only compound by like 1/10 of a percent or something?
Banks right now only pay about if you're lucky, 0.1%. Okay? So, where could you find an account that would give you 8% compounded quarterly? You could do a CD. CDs right now are maybe 2 or 3% if you're really lucky. Interest rates are ridiculously low right now. Okay? Now, the benefit of having low interest rates is, well, let's see, if interest rates at a bank are like, say, between 0 and 1%, what about mortgages? What about car loans? Yeah, they're pretty low too. Most interest rates right now are under 6%. Okay? So that saves you money when you're borrowing money, but if you put money in the bank, it doesn't really save you much. Where else could you put money that might grow at roughly that rate? You could put it in the stock market. What's wrong with the stock market? It can go up and down. But on the average, now first of all, does the stock market pay interest quarterly? No, it changes continuously, right? If you were to go back for the last 70 or 80 years, the stock market on average goes up a little less than 10% a year. It's probably right around, 9.5, somewhere in there. Okay? But definitely above 5, definitely above 6, definitely better than you could do at a bank. The problem is it's risky. Okay? Now, over the long haul, it continues to go up. So if you can put it in there for a long enough time and leave it there and then get out at the right time, people that needed to retire in 2007 and 2008, that was a really horrible time to try and retire. In fact, those portfolios, say you had $1 million, your 50 years was up in 2008 and you were ready to retire, that year the stock market lost about 40% of its value. Little more than 40%. I think it was about 47%. So if you had $1 million in 2006 and you were ready to retire, I thought, I'm going to wait a couple of years. Guess how much you had in 2008? Roughly. About half of what it was. Maybe a little more than $500,000. Okay? And it's taken the last 5 years in order to get back up to where people were. Okay? You heard the stock market, the Dow, hit its high again. Took it 5 years or so to recover from that. Okay? So it is risky, but let's figure this out. What if we put 9% in and it's compounded continuously, like a stock market account? We could get lucky and it just kept going up. Or maybe even with the bumps, on average, it's about 9%. That's going to be this formula. The amount is going to be PE to the RT. Now, the difference here is we know what we want, right? We want $1 million. So we put $1 million over here. We don't know how much principal we need, but we do know that we want that's 9%, isn't it? 9%, and then we're going to multiply that by 50. So again, get used to this. This stuff right here. What is it? What is it, Zach? It's a number. It's a very ugly number, but it's just a number. So if we want to get P by itself, let's divide by that. So this is going to be 0.09 times 50. E to the 0.09 times 50. So I get P equals this. Everybody watch, please. In your calculator, you can type this in. Most people would be pretty comfortable with this, 0.09 times 50. Again, make sure you type that in and put it in correctly, parentheses, all that. Would this work?
Yes. Except that's 0.08.
Oh, sorry. Would that work? It would, right? Because that's just moving the exponential into the numerator. So let's just double check and see. So I've got, clear that off. 1 million, and then I've got E raised to the negative 0.08 times 50. Thank you. Whoa. This says P equals 108 point what? 99. $11,100. So, on average, no guarantees in the stock market, but if you could come up with about $11,000 today, put it in the stock market and let it sit there for 50 years, you're going to have $1 million. What was it on the other one? Yeah, at 8% compounded quarterly, you'd need about $19,000. That compounding makes a huge difference. Now, the reason this is less is for two reasons. One, it's compounded continuously, and the other one is we got a higher interest rate. It was 9% versus 8% over here. Okay? Any questions? Okay, so in order to figure out these present value formulas, they actually have some the actual formulas in the textbook. But basically what we do is we take either one of these and we kind of solve them for P. Instead of figuring out what A is, plugging all this stuff in and figuring out what A is, let's solve them for what P is. Let's get P by itself. So if I did that, this is what I end up with. I end up with P equals, well, if I took A and divided it by this stuff, this would be 1 plus R over N raised to the NT. Well, what if I don't want this in the denominator? Let's move it in the numerator, and here's what I get. I get P equals A. You put in the amount that you want at the end. 1 plus the interest rate divided by, N, R over N. And then raised to the NT, except for we need to do what? Because we're kind of going back in time or reversing time. It's going to be a negative exponent. So if I solve this one, this would be P equals A, e to the negative RT. Now you'll notice, here's the amount that we wanted, 1 million. There's the E right there. There's the interest rate with a negative in front of it, and there's the time we gave ourselves. So these two are the present rate or the present value formulas. Again, they're the same ones we worked with a second ago. They're just solved for A rather than solved for P. Or the easy way to think about it is always put that number in front, and then if you want the future value, leave the exponent positive. If you want to go back in time and figure out how much you would have needed at the beginning of that, put a negative in front of it. It's pretty easy. Okay, are there any questions? Sure? Okay, let's take a look at the last couple and then we'll talk about this rule right here. It says, pay close attention to the following problems. They'll help you prepare for the next section. Next section as in section 6.8. So you're going to want to think about these. If you can get these ideas in your head, how these exponentials work, you're going to be much better off in the next section because these are going to be some story problems. It says this. How long would it take to double an investment if the interest rate was 3% compounded quarterly? We want the amount to double. Now, let me back up before we answer this question. Let's say, because you're all having heartburn, gosh, I wish I had $19,000, or I wish I had $11,000 to put in the stock market right now. I worked last summer. I've actually got, let's say, $5,500, which is exactly half of $11,000. $5,500 is a lot of money, but you could earn that much in a summer. Work hard, you could earn $5,500. Let's say you put that much in that account. Now, if you put $11,000 in after 50 years, you get $1 million. What if you only put $5,500 in? You get $500,000. If you start out with half of it, you end up with half of what the other sum would have been. Okay? So what we want to do on these problems right here is we want to figure out how long would it take me to double my investment? Does it matter how much you put in? Not as far as doubling goes, it's still going to double. So if you put in $100 and you double it, that's going to be $200. Hold on, did you put it on my desk? Okay, did you take like 2 more minutes? Okay. If you put in $100, your doubling is going to be $200. What if you put in $10? It'd be 20. Okay? So, would you guys over here, you put in $100. How much needs to come out? 200. Okay? Would you guys solve that? That's going to be 1 plus 0.03 divided by 4 in this case. Okay? 4t. Because we don't know the time, right? Would you guys over here, would you put in, let's put in $10. When you're done, you should have $20, right? This is going to be 1 plus 0.03 divided by 4 raised to the 4 times. Well, we don't know how much time, so let's put that in. Want to make sure everybody's on the right track. If we were doing this one, what's the first thing you'd do? You'd divide by 100. So we end up with 2 equals 1 plus 0.03 over 4 raised to the 4t. Okay, over on this side, what do you do first here? Same thing, you divide by 10, right? Okay, what I want you to take a look at is this. Aren't you at this point solving the exact same equation?
Yes.
Yeah. So it didn't matter if you started out with 10 and changed it to 20, started out with 100, changed to 200. In fact, you could do this. What if I started out with p? How much would be in there if I doubled it? 2p. And then it's going to be 1 plus 0.03 divided by 4 raised to the 4 times t. If I divide both sides, I end up with 2 equals 1 plus 0.03 over 4 raised to the 4 times t. Now, I'm going to erase some of this work. Does everybody agree that regardless of whether we start with p, 10, or 100, we end up solving the same equation?
Mm-hmm.
Everybody good there? Okay. I'm going to erase all of this, and we're just going to solve this guy right here. So once I have it to here, what do I do next? You do have to do something with logs, right? I've got to get this down where I can work with it. The variable is up in the exponent, so I've got to get that down. Marissa, which logarithm are we going to use?
Ellen. You want Ellen.
Do you really want to use log base 1 plus 0.03 divided by 4?
Simpler.
We're going to use ln. So this side's going to be ln2. If I take the ln of this side, they all have that same property. I can move that down where I can work with it. So this side's going to be ln2. This is going to be 4t ln 1 plus 0.03 divided by 4. Now, I want you to take a good look at this. Okay, don't say anything out loud. I'm going to ask Zach to answer in just a second. Maybe not Zach, maybe somebody else. But look at this right here. Zach, what is this? It's a number. Tylin, what's this? That's just a number. Okay? Marissa, what's this? It's a number. It's an ugly number, but it's still just a number, right? So here's where I am. I have, let's say this is a 7. 4 times x times 32. And I want to get x by itself. How would I get x by itself there? Divide by the 4 and divide by the 32, right? So we're going to do the same thing here, or the equivalent here. I'm going to divide this side by 4 ln 1 plus 0.03 divided by 4. Do the same thing over here. 4 ln 1 plus 0.03 divided by 4. Those are all going to cancel off. I'm going to be left with a t on this side. This is the exact answer, but we want some estimate for the time. So let's type into our calculator ln of 2, and then we're going to divide by that other stuff. Now, you do want to be a little bit careful. ln 2 divided by, what do I type in next? Parentheses, very good. There's more than one term or factor in the denominator, so I want to make sure I'm doing that right. That's going to be 4 ln, and then 1 plus 0.03 divided by 4. Any questions? Answer is 23.19. Yeah, we get your point. Come and see me. Your life is going to be miserable. Miserable. Come and see me. We'll talk about it. I'm dead serious.
I agree with her.
Okay. All right.
I just shut my mouth because I don't want to argue with you.
Okay. You seriously, don't do
I
it.
read it and I write H, so yeah.
Okay. You're gonna get yourself in trouble. Okay. Come see me. Yeah.
I think I did it wrong, but I don't know what I did wrong on my calculator.
We-
Because my calculator doesn't like it.
We can come take a look at it. Okay, let me finish this and then we'll look. Okay, let's look at this next one. This one is compounded continuously. So remember, this said it takes, what does this mean? About 23 years, right? Little over 23 years. Okay, let's take a look at 11% compounded continuously. So we're going to set it up like this. It's PE to the RT. If I put in P and I want it to double, how much do I get in the end? 2P. So this is going to be 2P. And look, regardless of whether you put in P or a number, when you divide by P, what do you end up with? You end up with 2. So this is 2 equals E, and our interest rate was 11%, and we don't know the time. Are you going to use ln now?
Yes, because it's basic.
Oh. So this is ln2, and this is 0.11 t. So what's the answer? ln2 divided by 0.11. And what do you end up with? What does it say?
6.3.
6 point what?
3.
6.3. And that would be in years. So it only takes about 6.3 years. Now, let's see. That's not too bad. You double your money. You put in 20,000, wait 6 years or so, and you've got 40,000. And then it would double again. Wait another 6 years, and it will double again. Then you'd have 80,000. Now, has anybody heard of the rule of 72? What is it?
It's like you divide it by 72 or something, and that shows you like how much it doubles.
Okay.
Boss explained
So,
it.
yep. So what it is if you take 72 and divide it by the interest rate, that is the approximate time needed to double an investment. Let's take a look at our problems right here. What if I took 72 and divided by 3? What is that? 24. What did we come up with? 23.19. Now, that's a heck of a lot easier problem to figure out. To say about 24 years, is that about 24 years? Yeah, let's do the other one. Let's take 72 and divide it by 11. What is that? 6.5? That's pretty close to 6.3, and we didn't have to deal with any exponentials or anything. Okay?
Are you saying we can do that on the test?
No, because we'd want an exact answer. Okay?
Oh, we can't use this on the test?
It's something to be aware of. It's not an exact answer. It's just an
Give us
approximation.
something, a shortcut that is so much easier that we cannot use on the test.
It's not an
You can
exact
check your work
answer.
that way.
There you go. Impress your friends, not your math teacher. Okay, so let's take a look at example 8. How long would it take to triple an investment if we invested at 8% compounded continuously?
Divided by 73.
About 9 years.
Says triple. Okay, there's not a rule of 72. Says triple. What, Parker, what is it? 3p equals e to the 0.08 times t, right? So notice what's happening every single time. Whether I started out with 100 or $10 or p dollars or whatever it was, if I'm doubling, it was 2p over here. If I'm tripling, it's going to be 3p. And notice that when I divide, I always end up with that number. If it was double, it's a 2. If it's a triple, it's a 3, and so forth. So this is going to be 3 equals e to the 0.08t. So that's going to be ln 3.08t. So t equals ln of 3 divided by 0.08. And approximately how many years is that? 13.73. So this is about like a stock fund. 8% is pretty darn good. If you can put your money in the stock market for about 13 or 14 years, it's going to triple in value. And at your age, you've got tons of time for doubling and tripling and all that sort of stuff. That's why it can grow to, that's why $11,000 can grow to $1 million in 50 years. And you don't have to do anything to it, just put it in there and leave it. Okay, questions?
Yeah, where'd that negative?
What?
Negative.
That's a decimal.
That's what I was trying to say as a point.
Okay, any questions? Okay, last problem. I want you to figure this out. You borrowed $2,135 from your parents to buy a car. They charge you 4.75% interest compounded monthly. They tell you don't have to make any payments, but you need to pay them back in 2.5 years. How much will you need to pay them?
Why would your parents let you borrow money?
There are lots of parents that charge interest.
Yeah, why did parents let you borrow my
What kind of character building experience would that be if you just got given money every time you turned
Oh my
around?
gosh.
Are you kidding me? That did that hard. My parents would say, "Oh, I have all my own money, Mom and Dad."
Okay, hypothetically speaking, maybe not you, maybe it's your friend and they ask you to compute the interest. Go ahead and figure that out.
Oh yeah, because we're gonna do that.
What's that?
Because we're gonna do that for them.
Of course you are, because you need a ride to school. And you don't want to pay for gas for the first month. How do you know which formula to use? What word is missing? If it doesn't say continuous, you're not using the one with the E in it. You're using the one that looks a little bit uglier. What's our principal?
Principal was 21.55.
21.35. Our interest rate was?
0.04.
Yeah, there we go. So we're going to do 0.0475. Compounded how often?
Monthly.
Monthly, 12. Raised to the 12 times. How many years?
2.5.
2.5, so 2.5. That's going to be 30 times, and 2.5 years is 30 months. So that's why that exponent is going to be 30. So if you type that into the calculator, roughly, how much do you have to pay your parents back? 2403 what? That's not bad. That's only a couple $100 in interest. Okay.
2 years.
Or a high school student, that's a lot.
Yeah.
I know people who lend their kids money and they charge them interest.
My parents might even try to lend me money.
You lend your parents money, and do you charge them interest?
Oh my gosh.
Oh, come on,
Very
I need
good.
parents' interest. I'm gonna start doing that to my parents. It's like, okay, you want me to do this for you? Fine.
I have a hard enough
Okay.
time getting it
This
back.
plus the interest.
All right, listen up. Listen up. Any questions? Okay. The things that are going to have you in the best shape for figuring out tomorrow's section are these problems right here. You really need to think about these right here. Again, it didn't matter whether we started off with $10 and doubled it to 20 and computed it. We ended up solving the same equation. $100 to $200 ended up solving the same equation. Okay? Or here, you'll notice that we started out with P and we just wrote 2P. And once we divide by p, this is what we're after. We end up solving that equation right there. If it was tripling, we started out with p, but once you divide by that p, you've got a 3 over there. Or another way to think of this would be, well, gosh, this is like putting in $1, and it triples to $3. Or putting in $1, and it doubles to $2. Okay? That's going to be very valuable when we start solving the equations for tomorrow. Any questions? Sure? Okay, this is due tomorrow at the beginning of class. So if you've got a question, you better come and see me. I have a class at 7:30. I've got a break from 9 until 10. And then I've got don't have a class again until this class. So there's lunch. I do have an SEO, parent-teacher conference tomorrow, but there's any time between lunch and 1:30. So make sure you come and ask. Marissa, can I see your work?